Okay, good morning everyone. So last week I sent the recorded lecture for isolated footing using a 4 meter by 4 meter meshing size. So ito din yan. It's the same model. Yeah. Okay. So although meron na akong recorded lecture for math foundation, so we will discuss pa rin, no? So it's a 4 meter by 4 meter. Let's now assume na math foundation naman. Okay. So it goes to show na ganun ka-flexible ang plates, no? So last time our lecture is about simply supported plate, di ba? Or fixed na plate, no? Steel plate, no? Ngayon, it's now math foundation. Last week, isolated foundation, no? Isolated footing. Now, it's math foundation. Okay? And with that, you can now see the flexibility or the extensive use of finite element using plate element. No? Although, as I was saying, always, the plate element that we are using is just the, sabihin na natin pinaka-primitive pa, no? 12 degrees of freedom. No? 12 degrees of freedom. Yeah. Actually, we can also use the triangular, no? We can also discuss that. No? However, ang limitation kasi ni triangular is yung constant strain, no? So meaning hindi maganda yung output niya ng strain, no? Kasi constant eh. No, ibig sabihin in an element, iisa ng strain yan. No, unlike yung plate natin, rectangular plate, yan, so nagbabago yung yan. Yung strain niya. Okay? Although si STAAD may ganon, but I believe no yung mismong element ni STAAD, and I also said it, na mas advanced, no? Kasi syempre it's a commercial software, no? Such that for example, yung minodel natin na let's say 4x4 na element, 1 2 3 4. Yeah. Then I loaded a midpoint load, nakuha pa rin ni STAAD yung exact answer, right? No, almost near the theoretical. However, when we do that, the same model, the same meshing, using this one, 12 degrees of freedom na plate element, rectangular plate element, we were not able to come up with the same answer, right? So that means mas advanced yung element na ginagamit ni STAAD, no? I think meron pa siyang node sa gitna. So such that, so kung ano yun, 1 2 3 4, apat, lagyan mo pa ng another node sa gitna, so 8. So that's already 8 nodes times 3. So that will be 24 degrees of freedom. So ganun siya mas accurate, no? More accurate than just using 12 DOF. Okay? Now, in order to get the same answer, no, with the STAAD, no, what we did is ni-refine natin yung mesh into smaller size, di ba? Ganun, no? Instead of 4x4, ginawa natin siyang ano ba? Basta hindi yata 4x4. 4 elements pala, I mean. 4 elements nakaraan, no, which does not pero kay STAAD nakukuha niya, no. So what we did is ginawa nating 16 element pala, no. Yun yung nangyari. Ginawa natin 16 element to come up with a more accurate result. So and it turns out to be true, no. So the same logic i-apply natin sa foundation. Okay? Although hindi ko lang diniscuss sa video, this is a 4 meter by 4 meter footing, no? Na una, I designed it first sa, what do you call this, sa spreadsheet, di ba? Using spreadsheet, using an isolated or rigid body. Ang tawag doon is rigid analysis pala, rigid analysis, no? Meaning hindi siya FEM, syempre, no? Manual calculation. Simpleng ano lang siya, P over A plus 6M over BD squared in order to get the stresses at the bottom of the footing. Okay. Yeah. So, rigid analysis lang yun. Yung nasa spreadsheet na yun. And hindi ko yata napakita doon sa recorded lecture na I was able to check the base pressure. No? Kasi, ganun din sa FEM. No? When you, ang nangyayari sa FEM is you should have a prior result. No? You should have a prior knowledge for the possible result bago mo i-FEM. Ganun siya ka-meticuloso, no? Na unlike the rigid body analysis na yan, simpleng P over A plus 6M over BD squared, ibibigay na niya yung stresses, di ba? Using manual ano. In FEM, hindi eh. Ibibigay niya yung stresses, ibibigay niya yung base pressure, but you should have an idea kung ano yung magiging base pressure niya. Okay? So, that means, before you do an FEM, you perform first a manual calculation. Just like the way I did doon sa video. No? Kasi, for example, nag-FEM ako, nag-modeling ako, nag-mesh ako ng 2 meter by 2 meter pala. Without knowing the possible base pressure, right? And definitely babagsak yun. Babagsak yun, no? Babagsak siya sa base pressure. Most likely, babagsak din sa displacement. And of course, pati sa moment, ma-overstress yung yung plate. See? So ganun si FEM, no? Parang it's like a checking na lang. Checking na lang si FEM, no? So ganun din yung practice namin when I was in a consulting firm, no, na syempre yung boss ko, no, iaano muna niya, no, i-manual check muna or they will ask me to perform manual calculation first, no, bago mo i-model. Kasi FEM is just a checking na lang siya. Checking na lang ng supposedly manual calculation mo. Okay? That's the idea. Okay? That's why this 4 meter by 4 meter, ginawan ko na siya ng calculation using a 1 meter by 1 meter mesh, no? 1 meter by 1 meter. And then, di ba, ang thickness natin dito is 700, 0.7. So that should be 0.7. So again, because STAAD is using a more advanced element in the plate, I believe it's of 24 degrees of freedom compared to what we are using, na 12 degrees of freedom. STAAD was able to come up with a more accurate result, no? Ganun siya ka-advanced, no? So ginawa ko na siya. Now, using our element, 12 degrees of freedom, hindi siya nag-work, no? Medyo, they call this, malayo yung displacement. Sa midpoint, okay, no? Pero pagdating sa what they call this, edge, umaangat na yung umaangat na yung what they call this, yung aking footing. No, whereas in actual, in STAAD, it's not, no. So that means may problem yung element ko. So that means I'm modeling it incorrectly, no. Hindi tama yung interpretation ng 12 degrees of freedom na rectangular plate element using a 1 meter by 1 meter mesh. Kasi imagine 4 meters yan, no? Tapos 1 meter, no? Medyo malaki yun. Medyo malaki yung ganong modeling. In short, as a practitioner, I advise, no, lalo na sa mga foundation, footing, I don't recommend a 1 meter mesh. Kahit pa mat foundation yan. No, I will not recommend a 1 meter mesh. Kasi, mga typical foundation natin, say isolated footing, 3 meters, di ba? 3 meters. I will not mesh it na 1 meter. No? So, that's why I modeled it using a 0.25 meters by 0.25 meters and using 12 degrees of freedom na rectangular plate element that we solved, no? That we are solving yung stiffness niya. It correctly computed the stresses, no? So that's what I'm going to show you. So that's it. Sige. So I'll just open my SMAT. Okay. So again, the support is 50,000 kilonewton per cubic meter. So ang computation niyan is so SBC natin, di ba, is 450 kPa. Again, this is just a supposedly, no? Supposedly it should come from geotech, no? Geotech dapat, no? But again, if you read Joseph Bowles, may mga correlation siya doon. No? 450 kPa. So kasi when I was a geotech, let's say we come up with an SBC of 100 kPa. Yun yung mga typical, no? Pag mga residential or 90 kPa. May ano kagad dyan. Automatic, ang allowable settlement niyan is around 25 mm. So, ganun kagad, no? So, that means, 100 kPa, 100 kPa kilonewton per square meter. So, with an allowable of, say, 0.05 0.025. Ayan, kung makukumpute mo na yung SDC niyan. Subgrade modulus. 100 divide 0.025. So that's 4,000. Okay, then multiplied by the factor of safety. Siyempre, when we come up with this SDC, may factor of safety yan na naka-attach. So times say 3 say 3 equals, so that's 12,000. Typical na yan. And when you refer to Joseph Bowles, basically ganyan. Ganyan din yung mga values, no? 12,000, medyo malambot pa nga yung 10,000, may mga 8,000 yan. Okay, so yung mga matitigas talaga na lupa, you can get as much as 20,000 pa kilonewton per cubic meter na subgrade modulus. Okay? So, but again, it should come from your geotech, no? And lalo na syempre when you do low rise, no? And most likely mat foundation ng mga low rise building, say mga 5-story. And may geotech ka na niyan, no? And part na ng soil report dapat mga ganyang kalalaking building, ganyan ka-expensive na building, it should have a subgrade modulus, no? So, you can see that yung mga ganyang 100 kPa, typical for residential, or 90 kPa with that kind of allowable settlement or displacement, the 12,000 is already on the average, no? The average. So, what more kung 450 kPa pa? No? Okay? So in order to get this, ang ginawa ko is 450 divide yun nga 0.0, say 0.025 nga. 0.025, 18,000, no? But syempre again, yung 25 mm allowable, no? What if less than that? Most likely less than that yung makukuha mong actual, tawag mo doon, displacement, no? Say displacement, no? Say 10 mm, no? Kasi ikaw as a designer, when you perform FEM, no? Hindi mo rin basta-basta i-allow yung 25 mm. So that's just an allowable. So gawin na natin mga 10 mm, no? Let's say 10 mm. If so, 450 divide 0.01, yeah, I'm already getting 45,000 kilonewton per cubic meter. Kaya ako ni-round up into 50,000. Okay? Yeah. Take note, this is 4 meters, no? 4 meter mat foundation, so medyo malaki-laki yan, no? Yeah. And by the way, how do we actually get the subgrade modulus, no? Yung actual nito is plate load test, no? So I was able to do that sa NAIA, no? Naging project namin yung NAIA 3. Kasi if you notice, may malambot na lupa sa NAIA, no? Nakikipag-ano pa ako nun, no? Nakikipagpatintero pa kami sa mga eroplano nun, ng Cebu pa. Kasi nandun karamihan ng Cebu pa. Kasi NAIA 3 is karamihan domestic, di ba? Domestic sa NAIA 3, karamihan, no? So nandun yung Cebu pa. Yan. So meron kaming, so one of the runway there, naglagay kami nagbutas kami diyan ng ano, they call this pit, no? Mga ano to? I think half, no? Kalahating tao siguro to, no? Anyway, basta ma-reach namin yung subgrade, no? Kasi makapal yung soil, makapal yung pavement, right? So mga ano siguro 'yan, yung pavement ng runway wala pa naman sigurong half meter. 0.5. Oh, mga ganun, no? Yan. So therefore basta ano 'yan, wala pang isang tao, no? Wala pang isang tao nakuha na namin yung ano, yung subgrade, no? Yeah. So yan, sa plate load test, if you read the ASTM standards, so meron ka dapat plates, steel plate. So ang bibigat niya, no, steel plates. Bawal kang ano niyan, what do you call this, matumbahan, no? Yan. Then you have a load here. Yeah. So you have a load there. And meron kaming dial gauge dito to measure the displacement, no? So yung load na yan, incremental mo ilo-load. So actually ang ano namin diyan, track. Meron kaming ELF track sa ibabaw, nandito yung gulong niya. Yan. So you're looking ano yan, elevation, no? Yan. So yung load mismo ng ELF track, yun yung mismo yung load namin. Then incrementally using a hydraulic jack, no? So meron kaming ano dito, may hydraulic jack, no, na nag-exert ng force sa ELF, and then of course doon sa plate, no? So then we measure the displacement, so you come up with a ganyan, a load versus settlement. Load deflection curve. Okay? And basically the subgrade modulus is yung slope, no? Yan yung slope, no? Okay. Anyway, in the literature, marami pa, may second modulus pa na tinatawag. So anyway, basically the slope, no, of that load deflection curve. Okay? So may kita mo naman pag malambot ang lupa, mali talaga yung subgrade modulus. So that's how geotechs obtain the subgrade modulus. The other one, mga correlation, no? Using soil test, correlation sa medium dense sand, sa clay, sa silt, may mga correlation yan. Yung iba naman, yung cone penetration test, no? Pwede rin yan, no? Pero at least itong plate load test kasi actual load yung nilalagay mo, no? So in KPA yan, no? So that's already for me, mas ano yan, mas standard yan. May ASTM standard yan, I mean. Okay, so I assume a 50,000 kilonewton per cubic meter, and then of course Y only yung option, because soil has no tension resistance, so compression only, and then plate mat. Then once you do that, select all the plates and then assign. Okay. And then for the loading, okay, so geometry, by the way, to show you, ito yung ating element, 0.25 by 0.25. Okay. And then for the properties, 0.7. Okay. So remember ano yung value ng concrete? The E is 21.7 gigapascal. So yan yung input natin sa ano, di ba? Sa MATLAB natin or sa SMAT code. Poisson ratio 0.17. Compared sa steel, it's 0.3. What else? Yun lang naman, no? The E and the Poisson ratio. Okay, and then specification, wala naman. Sa supports, take note, hindi ako naglalagay ng uplift load, no? Kasi nga, pag naglagay ako ng uplift load, which is, let's say, from analysis, madalas may uplift load, no? Let's say, kung meron kayong earthquake, no? Non-linear na yun, no? Hindi na siya elastic, no? So, yun yung limitation so far nung ginagawa natin, no? Because it's already an advanced analysis na yun, no? So, kasi, pag umangat yung footing mo, let's say, ito yung, di ba, ito yung plate mo. So, aangat yan due to an uplift load. So, iba na yung stiffness niyan compared dun sa foundation na completely resting on the soil. Right? Kasi if it's completely resting on the soil, yeah, so its stiffness is the whole system, the whole structure, the whole body. No, unlike ito, you will iterate, no, you will iterate stepwise, no, to obtain the stiffness of this portion, no. So iba ano yan, mas advanced na yan, advanced analysis na yan. Okay? So dito lang tayo. So, ganyan lang muna tayo. Okay. And loading. Ayan. So loading. So binabaan ko yung mga loads because remember dun sa isolated footing, 4,000 kilonewton yung max doon, no? So kailangan kong babaan yung mga they call this concentrated load para hindi lumagpas dun sa base pressure allowable natin na 450 kilopascal. Okay? So 400 here, then 250 here, 300 dito, and then 500. So you can assume, no? You can assume that let's say meron kang structure na 4 supports here. Ito na yung mga corresponding reaction. No? Then nilagyan ko ng moment, no? Because to show na, kasi in the past, puro tayo concentrated load, no? So ngayon lalagyan natin ng moment to show you na kaya din ng, kasi nga kaya nga rectangular plate bending element, no? Nagbe-bend siya, no? So kaya niyang mag-accept ng bending na load. Okay? So nilagyan ko siya ng moment load, no? Para mas flexible, no? Mas actual. Pwede nga rin may MX, no, on the other side, no? So MZ lang muna ginawa. Yan. So may moment on the two nodes dun sa 400 and then sa 300. Okay, so kumbaga you have vertical loads. Yan. And then of course, moment here. Okay. Although in actual, again, pwede ka may moment on the other side, no? And moment here, moment here. Okay, so analysis and that's it. Yeah, pwede na nating analyze to. Okay, so let's now proceed to post-processing. Yeah, so our maximum displacement is 3.3 mm. Okay, over here. Then the minimum is negative 0.6. Ito. Okay. So why here? Ulitin natin yung loading natin. Balikan natin yung mga loadings. So 400 here. We have 400. And where's the 500? Ito yung 500. And then where's the 250? Ito yung 250. And then, of course, dito yung 300. So, nandito yung dalawang moment natin. MZ, no? So, ito yung global axis natin na Z. So, MZ is on this direction. So, yan yung MZ natin. 52 and 15. And when you check on the post-processing, yeah, so it makes sense, no? Because the maximum displacement is here because andito yung pinakamabigat, no? Pinakamalaking load na 500 kilonewton meter. Okay? And to check na walang uplift, no? Dapat negative lahat ng displacement. So mukhang negative naman lahat. Right? And if you will see dito no, as a user or as a designer, tingnan nyo, no, I assumed a 10 mm lang, di ba, na displacement for a 450 kilopascal. So I obtained a what they call this 50,000 kilonewton per cubic. I only obtained a what they call this this settlement or displacement of 3 mm, no? So pwede mo pang pababain yung what they call this yung subgrade modulus mo, no? So to satisfy yung 10 mm sakali, it depends on you, no? So I have my subgrade modulus, tapos ito yung assumed displacement ko, and supposedly galing kay geotech, no? Tapos ito lang yung settlement ko. So yun yung i-check nyo, no? Dapat with your assumed bearing capacity and subgrade modulus, masatisfy mo yung yung settlement na assumption. Okay? Okay, so sa displacement pa lang yan. How about sa base pressure, of course? So plate results, base pressure. And apply. Okay. Ayan. So here it's 34 kilopascal up to 165. So talagang so talagang kaya, no, nung yung soil, yung loading. For example, no? So yun din i-check nyo, no? Make sure na hindi nyo ma-exceed yung allowable base pressure or bearing capacity. So basically, yun yung yung two service condition, serviceability requirements. Kailangan nyo i-satisfy. And lastly, the moment. Okay? Siguro, so with this, before I proceed sa SMAT or MATLAB, sige, let's have a 2 to 3 minute break. No? So, i-absorb nyo muna lahat noon. Okay, so let's now proceed with our SMAT. Although I'll try, no, kung kakayanin pa rin nung SMAT yung 256 na element na to, no? But first, let's proceed with getting the stiffness matrix of a single plate, no? Yung single plate natin. Okay, so that's 21.7 gigapascal, Poisson ratio of 0.17, and thickness of 0.7, and yung mesh natin is ito, 0.25 by 0.25. Yeah. And that's it. Ito na yung ating stiffness matrix. Yan. Supposedly ito. Yan. Okay. However, sabi nga natin, we have a spring, no? Saan ba yung open ko lang. So why 78,1,250? Kasi nga this is 0.25 by 0.25. And then meron ka tayong spring dito, di ba? Yan. Spring. And subgrade modulus is, we need to find its K. K na yan. The subgrade modulus is, lagay ko na lang sub, 50,000 kilonewton per cubic meter. So multiply natin by area. So each spring here has a tributary of this. Right? Yeah. Yan yung tributary niya. Which is half of 0.25. So that will be 0.125 by 0.125. So, yeah. So, our K is that. Yun yung formula na. Subgrade times the area. So, using that, I'll get 50,000 times 0.125. So, I'm getting 781.25 kilonewton per meter. Okay? So, convert into Newton, kaya naging 78,1,250. So, remember, we are getting the stiffness of this plate. Itong 12 by 12 na to. Yan yun. And the K with this vertical spring is addition dito sa, di ba? Ito, 1, 2, 3, this is 4, 5, 6, 7, 8, 9, 10. So this one is the stiffness of the plate in the vertical direction. No, ito din, teka, makita ko ha. Sorry, ito pala. Saan ba yung, ito, yan. Minimize ko para makita nyo yung 12. Yan. So 14710, no? Because itong stiffness na yan, the vertical yan. So, ano yung pang-apat? 1, 2, 3, 4. 1, 2, 3, 4. So, ito din. That's the vertical. 5, 6, 7. 5, 5, 6, 7. Ito din. And then 10. 8, 9, 10. 8, 9, 10. Yan. So, yan. Yung mga values na yan, yan yung stiffness ng plate natin on the vertical displacement. Okay? So, we need to add the additional stiffness from the soil. From the additional stiffness from the soil. Okay? So, yeah. So, sulat natin, no? So, dating 3.7, 3.6, 1.43, tsaka 1.55. And then, finally, adding the additional stiffness. Kaya, tinan nyo, no? In-update natin yung K11, K44, K77, and K1010. Ito. Yan. So, from 3.7, naging, sorry. So, from 3.7, naging, nadadagan lang siya. No? 3.7625. Ito naman yung 3.6375. Ito yung 1.43. Then, 1.55. 10, 10, 11, 11, 12. Okay? Ano ba siya dati? 7625, 36375. Anyway, so calculate ko muna. Update natin. Recalculate. Although I doubt na kayanin ni SMAT yung 256 by 256. Kaya ako nag-MATLAB eh. Okay. So after that, kopyahin natin to. Copy this. And then, paste natin dito. Yeah. Okay. However, dito yung ano. I don't know kung kakayanin yan. Foundation. Ito ba yun? Try this. Sige. Saka ko na lang i-try. No? Anyway, once you paste it here, let me share my screen. Yeah. Yeah. So what we have now is a stiffness of a single plate, no? But remember, it's 256, no? So ganun siya kadami, no? So let's say this is your plate. 1, 2, 3. So ang ating number of elements is 256. And a number of nodes is, ano nga yun? Na-discuss ko na to eh, di ba? Sa modeling. $289. That's 289. So 289. So we will be getting a stiffness of 289 times 3. $867. So it should be an 867 by 867. So ganyan kalaki yung matrix size na pinag-uusapan natin. No? Then, again, P is equal to SD. So 867 by 867. Of course, your force vector will be 867 by 1. So your displacement D is an 867 by 1 vector. Okay. So from a 12 by 12, paano ko ba yan? Say, so, di ba? Kumbaga ito, this is a 12 by 12. Yan. So lahat yan, meron kang stiffness matrix na hanggang 256 na elements. And then they will come up with a stiffness matrix of a 867 by 867. And when you form that, invert that matrix, and then with the force vector 867 by 1, so you will get the displacement. Okay, so let's try that in our MATLAB. No? Again, pinakita ko na before na it's the same code na ginawa ko sa SMAT, right? It's the same, no? It's such that, however, sa SMAT is mukhang hindi niya kaya, no? Kasi yan, siguro, hihirapan siyang i-process yung 256, no? Okay, so let's say make this 256, tapos paste ko dyan yung nakuha natin dito. So, Control C, then paste here. So nandito na rin yung ano, I think ito na rin yun. Wala pala akong incidence dito. Okay. Hindi, ito yata. Yeah, ito pala yung incidence ko. Ito yung incidence ko. So, to quickly get the incidence, no, you proceed with the plate layout. Plate layout. Yeah. So, ito yung incidence ni STAAD. 1, 2, 4, 3. Kasi ninyo, no? 1, 2, 4, 3. Oh, sorry. So if I draw this, it's 1, 2, 4, 3. So yeah, it's clockwise, right? But ang problem ko dyan is, sabi ko nga, ang derivation natin, if you remember, is clockwise, pero dito yung node 1 natin, right? Ay, sorry, nag-interfere. Nandiyan yung node 1 natin. So, yun yung ginawa ko. No? So, to be consistent with our derivation. So, instead of 1, 2, 4, 3, I will use 3, 1, 2, 4. So, so this is 3, 1, 2, 4. So, with that, after, let's say, kinapin nyo to, pinaste ko siya dito. Yan. So, sinwitch ko lang yung position ng 4 and 3. No? So, yung 3, kinuha ko sa harap. Okay? Because may formula ako to set up the corresponding incidence. Diba? If this is node 3, ano yung ano niya? DOF niya. That will be 7, 8, 9. Right? This is node 1. Ang incidence niya is 1, 2, 3. Node 2, 4, 5, 6. And 4, 10, 11, 12. Gets nyo naman yung formula, no? So 4 times 3 is 12. 4 times 3 minus 1, 11. 4 times 3 minus 2 is 10. Okay? So yun lang yung formula. And with that, drag down hanggang sa last element. So this is your incidence. Okay? Because you will need that in your SMAT here. Okay, so if I have to update this, it should be, I don't know, kaya niya. So number of nodes is 289. A member is 256. Ano na-complete ko? 867. Then, saan manggagaling yung incidence? So, under siya ng sheet number 2 from I4 hanggang T259. I4 hanggang ito. I4 hanggang T259. Okay, then it's located sa sheet number 2. Right? Sheet number 2. Okay. So, ignore ko muna itong B. Hindi naman siya nagmamatter sa ano. Yan. So, ito na yung gagawa ng stiffness matrix. Itong S4. And get the S4 inverse. Let me try. No? So, save. Let me try kung magagawa niya. Recalculate. Yan. So, nag-green siya, meaning, kinocompute na niya yan. Ongoing na yung computation ni SMAT. Sige, let's try to wait, no, kung kakayanin. Okay, so mukhang di kaya. Although, yeah, nandito na siya sa inverse, no? Tinatry niya mag-invert matrix. Okay, tapos na siya dito sa ano. Ibig sabihin, nakuha naman niya yung stiffness. Tapos na siya dito eh. So, yeah. Ini-invert na niya yung matrix. So, dun siya nagtatagal din. Anyway, so let's try to do it in MATLAB. No? Sana hindi maghang. Okay, so in MATLAB, it's the same code, except syempre iba lang yung coding mismo, pero it's the same formula I use. This is the B matrix, the B transpose, this is the thickness, 0.7, the size of the mesh, 0.25, the Poisson ratio, 0.17, the elasticity na 21.7 gigapascal, same formula for the rigidity, or the D matrix. Yeah, so same formula for stiffness matrix. And then for the addition of 1, 4, 7, 10, this is the soil subgrade modulus stiffness, 78, 1 to 50. Yeah. So this will also try to come up with the same stiffness matrix. So, and then, kasi tuloy-tuloy na to eh. Then for the forces, ito nga. We minimize this. And then this is STAAD. Loading. Yeah. So as you can see, ito yung mga node numbers, no? 65 to 35, and then this is the what do you call this? MATLAB. So let's say the 400 is here, node 55. Okay, so ano yung DOF niyan? So that will be 55 times 3. No, but we will subtract 2 to get the DOF. Minus 2, 163. So this 400 kilonewton is applied at DOF 163. Okay? Then remember may moment tayo dito na 52 kilonewton meter. So force at DOF 165 siya. Remember yung numbering natin ng DOF per node 163, 164, 165. Okay? So yung moment about Z is the last DOF. Okay. How about 250? I think 250 is here. Ito. So 250. So ang DOF niya ay, this is node 235. So same formula, no? 235 times 3 minus 2, 703. Yeah. So it's the same, 703. Next, 300 kilonewton here. Node 65, same formula, 65 times 3 minus 2, 193. Okay, and then the moment is applied at 193, 194, 195. Okay. And lastly, this is the largest vertical load, yung 500, no? Node 224, same formula, times 3 minus 2, 670. Okay? Ayan. So basically, the code earlier is to get the S matrix, we now have the force matrix, so we can now find the displacement, S inverse P. Okay. Anyway, to set up the force vector, remember, you can just declare kay MATLAB yung matrix na to. So the force vector is having a size of all zeros, na ang size ay GDOF, 1. Remember, ang GDOF natin ay 867, which is a function of the number of nodes na 289 times 3. So, yan yung GDOF mo. 867. So, lalagyan niya ng puro 0. Tapos, with this command, fill upan niya yan ng values. Okay? So, tingnan nyo, yung SMAT, di pa rin tapos, no? So, I'll try to run this. Tingnan nyo, tapos agad si MATLAB. So, tapos na si MATLAB, si SMAT nagra-run pa rin. So, ganun kabilis si MATLAB. Well, syempre, ano to, remember, SMAT is a freeware. Freeware yan. So, ang advantage lang niya talaga yung mga presentation, calculation. And that's it. Teka, linisin ko muna. Okay, so this is the deformation, no? So let's check. So ito nga ulit yung maximum displacement natin. So what's the maximum displacement? 3.3. Node 273. So using the formula 273 times 3 minus 2. So to get the DOF, times 3 minus 2, 817. Okay, so yan yung DOF, 817. So let's check. It should be 3.3. So displacements, 817. Okay, so we're getting the same displacement. No, 3.3. Okay, how about so itong pinakamaliit. So that's only 0.68 millimeters. Node 68. So using the same formula, 68 times 3 minus 2. 202. Let's check. Palitan ko lang to ng 202. Yan, 0.68. See? It's 0.68 millimeters, which is consistent kay MATLAB, kay STAAD. Okay, we're done with the displacements. How about the base pressure? No? So, sa base pressure, so ito yung pinaka, ano ko dyan, calculation. Yan. Yan. So, so you can imagine if this is the whole mat foundation. So, meron tayong mga spring, and with the corresponding displacement na nakuha na natin, of course, this displacement, remember yung simple formula, you know the displacement, right? You know the stiffness, you can get the force, diba, of the spring. The spring stiffness is 78,150, diba? Kilonewton, Newton per meter. And with the known displacement in meter, you can get the force at each spring. So therefore, to get the pressure, simply the force, so pressure is force over area. Okay, so force this 78,150, times 1,000 to convert into millimeters, no? And then the displacements, which we can easily find, di ba? Yung kanina ginawa natin. Why 4? Because yeah, because 670. Ito, a squared because per plate has a dimension of a and b, right? Pero ang ginagawa natin, a and b is the same, so a squared. Okay? Yeah. So bakit 4? Kasi remember, each plate has 4 spring. Yeah. So meron tayong 4 na spring, and then times the displacements divided by the area. Okay? Yeah. So anyway, maliliit naman yung mesh natin. So if ever na 1 meter by 1 meter yung mesh natin, medyo hindi magtutugma yan madalas, no? So that's why this is an advantage of creating a fine mesh or a very small mesh. Okay? So with that formula, so copy ko to, paste here. Tapos let's say we wanted to find out the base pressure of plate results, base pressure. Yan, ito na yung base pressure, di ba? So let's just check plate 51. No, plate 51, for example. Plate 51, if you refer here, dito sa ating contour, ito si plate 51, di ba? Pure yellow. So nandito yung base pressure natin. Around 124 to 133. Right? So let's sulat natin. 124 to 133 kPa. Okay? So that's plate 51. So palitan ko to. Sorry. Gawin ko tong di pala. Nodes pala yung kailangan ko. Node 71. Node 71, which corresponds to what DOF? 71. So 71 times 3 minus 2. 211. So palitan ko to ng 211. So, make this 211. Okay? Pinalitan ko ng displacement. Ibig sabihin, ang gagamitin niya to compute the base pressure is the displacement at node 211, the average displacement. Yeah. So I'm getting 131 kilopascal, which is, right, as you see, on the interval of 124 to 133 kilopascal. Okay? Ano nangyari sa SMAP natin? Nag-invert pa rin siya ng matrix. Okay. And then, what else? Base pressure. So, kaya tayo sa yellow, how about ito, itong ano? Itong medyo red to. So, that's about 165 kilopascal, no? So, yan. So, node 256. Hindi, yung loob na lang. 240. Node 240. Palitan natin. Alisin ko na pala to. Yan, node 240. So, 240 is, anong DOF yan? 718. Yan. DOF 718. Yan. 153 kilopascal. Okay? And if you look at the contour, yeah, It's about 150 kilopascal. Nandito tayo sa ano. Okay? So displacement, base pressure, okay na tayo. Then lastly is for the moment. Plate results, global moment, kahit mx na lang. Okay? So as you can see, this is the global moment. So meaning ito yung mga positive. So kumbaga, if I come up with a section plane there, ito yung magiging contour natin. Something like this. Right? Kasi nandito yung load natin eh. So negative moment yan. And ito yon. Ito yung mga portion na to. Yan yung mga negative moment natin. The magenta and blue. Okay? And here, that's a positive moment. Okay? Yung red. So ito siya. Okay? So let me check. By the way, how do we compute for the moment? So this is the formula. Yeah, na discuss na din natin to last example. Yeah. Okay. Mas maganda kasi sa SMAT para naalala nyo. Yan, okay? So ito yung formula natin ng moment. Once you get the displacement, no? Babalik mo lang yung constant D matrix, the B matrix, then a constant phi inverse matrix. Di ba? So lahat to nakuha na natin earlier. Ibabalik lang natin do sa displacement nung plate. I-extract mo lang yung displacements ng plate. Remember, meron tayong 12 displacements per plate. So ibabalik mo lang yun dito to come up with the moment of your plate. Okay? So yun din yung ginagawa nitong code na to. Okay? Yun din, no? So then kinonvert ko siya into STAAD using this formula. Sorry. Yan, using this formula. Divide lang sa area or sa A squared. Okay? And then so that's it. So let's proceed here. So for example, double click. Yan. So this is plate 215. Yan. Plate 215. So 71 and 2 kilonewton meter per meter, which is consistent dito. No, that's near 71. No, ito ano to? That plate 71. Okay. Let's check this. So STAAD. Copying ko na lang to. Yan. So anong element yun? 215. Okay. And that's it. So it's the same. I'm getting 70 and 2, which is I STAAD 71 and 2 kilonewton meter per meter. Okay. So okay tayo sa positive moment here. How about the negative moment here? Plate 210, 210. Okay, tayo kay MATLAB. Plate 210, 46 and 68. So kay STAAD, it's 42 and 69. Almost near, no? Okay. So tingnan niyo yung consistency, no? negative kay MATLAB, no? Meaning, magkaiba silang nung sign nung isang plate. Diba? Ito yung kinuha natin kanina. So magkaiba sila na sign. So meaning, it's true na this is positive moment, this is negative moment. So consistent, no? Even the signs. Right? And lastly, so yan, okay na tayo sa positive and negative. Siguro itong nasa gitna. Yan. 2, 1, 2, 3. Okay. Yes. 1, 2, 3. Yeah. So that is 34 and 37. STAAD gets 35, 34. Almost the same pa rin, no? Okay. So, yeah. So that's it. Do you have questions? So nakita nyo, no? So using the very primitive rectangular plate bending element, 12 degrees of freedom, no? So we were able to come up with the same result with a commercial software, no? It's STAAD, no? So meaning, for sure, even ETABS, even SAP 2000, MIDAS, you can employ the same FEM procedure we use, no? You can use, it's still very very in line with the commercial software, no? Yun nga lang, again, mas advanced kasi, no? Expected yon, mas advanced yung plate element na ginagamit nitong mga commercial software, because kaya nga commercial software, no, binabayaran natin. And of course yung GUI nila, post processing, no, but the theoretically, no, the finite element approach, the computation is there, no? Yun yung nalaman nyo, no? It's still the same, no? Mas nagiging, ang limitation lang natin is we are using a more number of elements to come up with the same result, no? Kasi nga, limited yung 12 degrees of freedom. Unlike the commercial softwares like STAAD, it's using a 24 degrees of freedom, no? Baka hindi lang, no? Na plate element. Okay, so that's it. So that nandun yung flexibility of FEM, no? So in this math foundation, isolated footing, no? Combined footing, lahat na, no? Kasi nga namo-model mo na, applyin mo lang ng load, no? Okay, even slab, no? Suspended slab, pwede rin, no? Nagiging ano lang talaga, it's more on ano na lang, in terms of software, so it's more on creating a convenient applying of load, no, convenient post-processing, no? But the main idea of this course is the computation, no? The theoretical computation, no? of the FEM, no? Okay, so we can now proceed with shells, no? Next time. So the purpose of the machine problem na I said, ano pala, gawin na natin 3 weeks yung deadline, no? The purpose of the machine problem is for you to know how many elements ang kailangan yung gawin, no? Parang ginagawa natin, no? To come up with the same result with the STAAD or with ETABS, kung yun ang gagamitin nyo, with MIDAS, no? So such that ma-realize nyo, no, how to obtain the result, no, using classical plate bending element. Okay, so L-shape siya, no? L-shape siya. Okay, 10-inch, no? I believe 10 inches, so that's just 250 mm lang, no? So kaya yun ng kaya siguro yun na 10 mm mesh, no? 10 mm. So try nyo rin 25 siguro. So yeah, doon nyo makikita, no? Kung same kayo ng result ni STAAD. Okay. So if no more question, siguro pwedeng maganda dyan, exciting dyan, no? Pa-machine problem din ako ng ganito, foundation, di ba? So get the reaction from the from the ano no, from your structural analysis, tapos apply mo sa ano, sa math foundation, di ba? So ganun eh, tuloy-tuloy na no? When you have the moment, kaya mo na rin bakalan. No? So another ano lang yun, coding na lang yun. Okay? So I'll just upload the recordings later and send you the link. No more questions? Sige, I think, kailan ko ba binigay yung machine problem this week? Pwede tayong hindi magklase next week, no? We'll see. Kasi may ano naman kayo, machine problem. Okay? Sige, so see you next time. Ano yung 4 files? Ano yung 4 files? Yung SMAT? Alam ko na upload ko naman siya. Sige. Wala pa naman akong binabago sa SMAT eh. Kasi pag may changes ako sa SMAT, ina-upload ko, I believe it. Sige, I will check. No? May G drive tayo. So that G drive is nasa Google Classroom. So you can always refer back sa location niya. Okay? Sige, so that's it. See you next time. Okay, bye.